The Earth is a mysterious place. From the deepest parts of our oceans to the edges of outer space, there's still so much we don't fully understand about the planet we call home. Beneath our feet, above our heads, and woven invisibly through the very air we breathe, there are systems at work that most people never think about, let alone notice. One of the most fascinating of these hidden systems is something known as the Schumann resonance. Considered by many to be the heartbeat of our planet, the Schumann resonance was only first mathematically predicted in 1952 by the German physicist Winfried Otto Schumann, a man who was working at the Technical University of Munich at the time and who, remarkably, never lived to see his prediction fully confirmed by instruments sensitive enough to measure it directly. To understand what the Schumann resonance actually is and how it comes to exist at all requires stepping back and building an awareness of some of the largest physical systems on our planet. It requires us to think about the sun, the atmosphere, the magnetic field that surrounds us, and the electrical storms that rage constantly somewhere on Earth at any given moment. In that sense, exploring the Schumann resonance provides a wonderful entry point into the much broader subject of atmospheric macrogeophysics. I'm your host, Stefan, and welcome to Geophysics Explained. Let's begin with the planet itself. The Earth is the third planet from the center of the solar system, sitting in what scientists often call the habitable zone, the narrow band of distance from the sun where temperatures allow liquid water to exist on a planetary surface. At roughly 260 trillion cubic miles in volume, Earth is more massive than its closest planetary neighbors, Mercury, Venus, and Mars. It is composed primarily of silicate minerals, layered around a dense iron core that generates the planet's magnetic field through the churning motion of molten and solid iron deep within. What makes Earth truly unusual, even unique among the rocky planets of our solar system, is the sheer abundance of water present in all three states of matter: solid ice, liquid oceans and rivers, and vapor suspended invisibly in the air, existing simultaneously within, on, and above its surface. This abundance of water, combined with a stable temperature range, has allowed something remarkable to happen: life. And life, in turn, has carpeted much of the Earth's surface in a rich blanket of vegetation, forests, grasslands, and plankton-filled oceans that quietly exchange gases with the atmosphere above them every single day. That atmosphere itself is a layered and complex structure, far more intricate than the simple blue sky we glance up at, composed mostly of nitrogen and oxygen, with trace amounts of argon, carbon dioxide, and other gases. The atmosphere extends far beyond what most of us imagine when we picture the sky. It doesn't just stop a few kilometers up. It thins out gradually, layer by layer, stretching outward for hundreds, even thousands of kilometers, before it truly gives way to the vacuum of space. The outermost of these atmospheric layers is called the ionosphere, and it begins around 1,000 kilometers above the Earth's surface, extending down to roughly 50 kilometers above the ground. Despite being classified as part of the atmosphere, the ionosphere behaves quite differently from the air we breathe at sea level. It is air, technically speaking, but air that has become extremely thin and crucially ionized, meaning that many of its atoms and molecules have been stripped of electrons by intense solar radiation, leaving behind a soup of charged particles that behaves almost like a fluid conductor wrapped around the entire planet. Above the ionosphere lies yet another invisible structure, the magnetosphere. This is a vast region surrounding the Earth where there is no meaningful atmosphere left to speak of, but where a powerful magnetic field, generated deep within the planet's iron core, continues to exert its influence far out into space. The magnetosphere plays a critical protective role for life on Earth. It acts as a shield, deflecting much of the constant stream of highly charged particles that the sun ejects outward in what is known as the solar wind. Occasionally, the sun releases much more intense bursts of these particles during solar flares and coronal mass ejections. It takes roughly 8 minutes for light from these events to reach us, but the charged particles themselves, being made of actual matter rather than pure light, arrive later, sometimes hours or even a day or two afterward, depending on the speed of the ejection. When these particles finally reach Earth, they begin to interact with the magnetosphere, and rather than striking the planet head-on, they are guided and funneled along the invisible lines of the magnetic field down toward the poles. This is precisely why we see the aurora borealis in the northern hemisphere, and the aurora australis in the southern hemisphere. Those shimmering, rippling curtains of green, pink, and violet light that dance across polar night skies are, in essence, the visible signature of charged solar particles slamming into and exciting the gases of our upper atmosphere. During particularly intense solar storms, this auroral activity can be pushed much closer to the equator than usual, occasionally allowing people at surprisingly low latitudes to catch a glimpse of the phenomenon. As these solar ejections press against the outer boundary of the magnetosphere, they don't simply bounce off cleanly. The field lines themselves become warped and distorted, compressed on the side facing the sun and stretched out into a long tail on the side facing away from it. This constant pushing and pulling doesn't stay contained at the outer edge either. It presses inward, influencing the ionosphere and the deeper layers of the atmosphere beneath it. The ever-shifting, ever-fluctuating nature of the magnetosphere is, in fact, one of the primary drivers behind the electric currents that flow through the ionosphere, and these currents in turn have a measurable influence on weather patterns closer to the surface. It's a chain reaction that begins millions of kilometers away on the surface of the sun and ends with subtle shifts in the electrical behavior of the air just above our heads. When charged particles accumulate near the Earth's surface, whether from these solar-driven processes or from the more familiar mechanics of evaporation, convection, and moisture movement within storm clouds, they can build up into powerful storms. Within the thunderstorms, positive and negative charges separate and accumulate in different regions of the cloud, and between the cloud and the ground below. At a certain point, the imbalance becomes too great for the surrounding air to insulate, and the two oppositely charged regions violently equalize. This is lightning. Enormous amounts of charged electrons discharge in a fraction of a second, tearing through the atmosphere and, in many cases, striking the ground directly. The bolt of lightning itself is almost unimaginably hot, hotter even than the surface of the sun for the brief instant it exists. And this intense energy release radiates outward not only as the visible flash we see, but also as a burst of electromagnetic radiation across a wide range of frequencies. Many of the photons generated by a lightning strike interact almost immediately with nearby matter, air molecules, water droplets, dust, and are absorbed or scattered within moments. But a portion of that electromagnetic energy escapes the immediate vicinity of the strike and begins traveling outward, away from the Earth's surface, moving at the speed of light. As these photons rise upward through the atmosphere, they eventually encounter the ionosphere. Because of the ionosphere's unique electrical properties, being ionized and electrically conductive, it doesn't simply let this radiation pass through into space. Instead, it reflects much of it, bending the photons back down toward the Earth's surface. When these reflected photons reach the ground or the ocean or whatever conductive surface lies below, they can reflect upward again, back toward the ionosphere, where the process repeats. In this way, a portion of the electromagnetic energy released by lightning becomes effectively trapped, bouncing back and forth within the narrow cavity formed between the Earth's surface and the ionosphere, roughly 50 kilometers of space acting as a natural waveguide. This trapped, resonating electromagnetic energy is what we call the Schumann resonance. The physics behind why this energy settles into specific, predictable frequencies, rather than just being a chaotic mess of noise, comes down to simple wave mechanics. Electromagnetic radiation, like all light, travels at approximately 300,000 kilometers per second. For a wave to resonate stably within a spherical cavity like the one formed by the Earth and its ionosphere, its wavelength needs to fit neatly around the circumference of that sphere, reinforcing itself with each pass rather than canceling itself out. When you work through the mathematics of a wave whose wavelength matches the Earth's circumference, you arrive at a fundamental frequency of approximately 7.83 Hertz. This is the foundational Schumann resonance, and it consistently shows the highest amplitude, meaning the strongest, most easily measured signal among all the related frequencies. But the fundamental frequency isn't the only one produced. Just as a guitar string produces not only its bass note, but also a series of higher overtones, the Earth ionosphere cavity produces higher harmonic modes as well, appearing at roughly 14.3 Hz, 20.8 Hz, 27.3 Hz, and 33.8 Hz. Each of these represents a wave pattern that fits a whole number of additional oscillations around the planet's circumference, layered on top of the fundamental tone. To put these frequencies into context, it helps to compare them to something more familiar. Radio waves, the kind used for broadcasting music and voice communication, generally sit at frequencies in the range of thousands to millions of hertz, and even higher for things like Wi-Fi and mobile networks. The Schumann resonance, by contrast, sits at an extremely low frequency, well below the range of standard radio broadcasting, in a part of the electromagnetic spectrum known as extremely low frequency, or ELF, radiation. And just like radio waves, this extremely low frequency electromagnetic radiation has the ability to penetrate through most physical materials, including, notably, the human body. This particular characteristic is part of what has made the Schumann resonance such a subject of fascination and at times speculation outside of strict academic geophysics circles. It's worth taking a moment here to appreciate just how difficult it was, historically, to actually confirm that this resonance existed at all. When Winfried Otto Schumann first worked out the mathematics behind this phenomenon in 1952, he was doing so purely on theoretical grounds, treating the Earth and its ionosphere as a kind of giant spherical capacitor and calculating what frequencies such a cavity should naturally support. It wasn't until several years later, in the late 1950s and early 1960s, that researchers were able to build sensitive enough magnetic field detectors to actually pick up the faint signal and confirm that Schumann's calculations matched what was really happening in the atmosphere. This was no small technical feat. The Schumann resonance is an incredibly weak signal, easily overwhelmed by the electrical noise generated by ordinary human activity, so early researchers often had to set up their measuring stations in extremely remote locations, far from cities, power lines, and other sources of interference, in order to get a clean reading. Even today, many of the research stations dedicated to monitoring the Schumann resonance around the world are deliberately positioned in isolated regions, places with minimal artificial electromagnetic activity nearby, precisely so that the faint natural hum of the planet isn't drowned out by the electrical clutter of modern civilization. It's worth pausing here to acknowledge something important about the modern electromagnetic environment we all live within. Over the past century, human civilization has filled the air around us with an enormous amount of artificial electromagnetic radiation that simply did not exist before industrialization. 60 hertz alternating. Current power lines hum quietly in the walls of nearly every building on the planet. Cellular networks, Wi-Fi routers, broadcast towers, and countless other technologies all emit their own electromagnetic signatures into the environment continuously. This flood of artificial electromagnetic noise has, in a very real and measurable sense, altered the background electromagnetic environment that we are exposed to on a daily basis. As a result, the natural signal of the Schumann resonance and its higher harmonic modes, while still very much present and still measurable with the right instruments, now exists against a much noisier backdrop than it did before the widespread adoption of modern electrical and communication technology. Scientists refer to this as a lower signal-to-noise ratio, meaning the natural signal hasn't necessarily weakened on its own, but the surrounding noise has grown louder, making the natural signal comparatively harder to isolate and observe without specialized filtering equipment. Despite this added background noise, the Schumann resonance itself remains remarkably stable and persistent, and the reason for that stability comes down to sheer statistical consistency. At any given moment, somewhere on Earth, a thunderstorm is almost certainly in progress. Across the globe, lightning strikes occur at an astonishing rate, somewhere in the range of 50 to 100 times every single second. This means the Earth ionosphere cavity is constantly, continuously being fed fresh injections of electromagnetic energy, never allowing the resonance to fully fade out before the next wave of lightning-generated photons arrives to reinforce it. It's a bit like a bell being struck so frequently that it never truly stops ringing. The individual strikes, blending together into a continuous low hum that circles the entire planet. Given the sheer complexity of the chain of events required to produce it, beginning with high-energy particle emissions from the surface of the Sun, cascading through the magnetosphere, while influencing the electrical currents of the ionosphere and ultimately connecting to the ceaseless activity of thunderstorms across the globe, it's easy to understand why so many people have come to think of the Schumann resonance as something like the electromagnetic heartbeat of the entire planet. As far as scientists can determine, the Schumann resonance is not a new or recent phenomenon at all. For as long as Earth has possessed both an ionosphere and an atmosphere capable of generating lightning discharges, this resonance has almost certainly existed in some form, quietly circling the planet long before any human instrument was capable of detecting it, and indeed, long before humans, or any life at all, existed to wonder about it. That said, the resonance is not perfectly constant in its intensity, depending on the distribution, frequency, and overall intensity of lightning activity around the globe at any given time, which itself shifts with the seasons, with regional weather patterns, and with the general balance of storm activity between the northern and southern hemispheres. The amplitude of the Schumann resonance can vary noticeably from day to day and season to season. Even so, the underlying frequencies themselves, that foundational 7.83 Hz tone and its higher harmonics, remain a permanent and ever-present feature of the electromagnetic spectrum surrounding our planet. Beyond the strict physics of the phenomenon, the Schumann resonance has also captured a considerable amount of attention outside of academic circles, and it's worth addressing that honestly, because its fundamental frequency of 7.83 Hz happens to fall within a range that overlaps with certain patterns of human brainwave activity, particularly the alpha and theta wave ranges, associated with relaxed meditative states of consciousness. The Schumann resonance has become something of a cultural touchstone in wellness and alternative health communities. It's often described in those spaces as a kind of natural frequency that the human body is inherently attuned to, sometimes marketed as the basis for relaxation devices, meditation aids, or even therapeutic sound recordings tuned specifically to 7.83 Hz. It's important to note that the rigorous scientific evidence connecting the Schumann resonance directly to measurable health outcomes or brainwave synchronization in a strong causal sense remains limited and is still very much an open area of investigation rather than an established fact. That doesn't make the underlying physics of the resonance any less real or any less fascinating, but it does mean that some of the broader claims circulating about its effects on the human body should be approached with a healthy dose of scientific caution until more rigorous, peer-reviewed research settles the question one way or another. Scientific understanding of the Schumann resonance, and particularly of how its subtle frequency patterns might influence biological systems or the broader planetary environment, is still very much a developing field. Researchers continue to study whether variations in Schumann resonance amplitude correlate with anything meaningful in terms of atmospheric conditions, solar activity cycles, or even broader climate patterns, though establishing firm, well-supported conclusions in this area remains an ongoing scientific challenge. What is a bit more concrete and genuinely exciting from a planetary science perspective is the potential for the Schumann resonance concept to be applied well beyond Earth itself. Because the resonance depends fundamentally on the presence of both an ionosphere and an active source of electrical discharges, such as lightning, within a planet's atmosphere. In principle, any planet or moon that possesses these same basic ingredients should generate its own unique version of this resonance, with its own fundamental frequency, determined by the size of that particular body and the properties of its own atmospheric cavity. This opens up a fascinating possibility for planetary scientists. The idea that detecting and measuring the equivalent of a Schumann resonance on another world could serve as a kind of remote diagnostic tool, offering clues about that planet's atmospheric composition, its electrical activity, and even whether it experiences storms similar to the ones we're familiar with here on Earth, all without needing to physically land an instrument on the surface to find out. There's also a broader lesson buried within all of this, one that extends past the Schumann resonance itself and speaks to something larger about how planetary systems work. What makes the resonance so remarkable, when you really sit with it, is how many seemingly unrelated processes had to align in order to produce something as simple and elegant as a steady 7.83 hertz hum circling the globe. You need a molten iron core deep within the planet, churning and generating a magnetic field. You need a star nearby, actively fusing hydrogen and releasing streams of charged particles outward into space. You need an atmosphere thick enough and layered in just the right way to form both a dense lower layer and a rarefied ionized upper layer. You need liquid water cycling between ocean, cloud, and rain, building the towering storm systems capable of generating lightning. And you need all of these systems to operate continuously, day after day, for billions of years, in order to produce a resonance stable enough to be considered a defining feature of the planet. In many ways, the Schumann resonance is less a single phenomenon and more a kind of signature, an audible fingerprint left behind by the combined activity of nearly every major system that makes Earth the dynamic, living planet that it is. It's a genuinely thrilling thought to consider, that somewhere out among the other worlds of our solar system, and perhaps even among distant exoplanets we've only just begun to study, similar invisible hums might be quietly circling other atmospheres, waiting for the right instruments and the right scientific curiosity to finally detect them. Perhaps future missions to Venus or to Saturn's moon Titan or to the ice giants further out will carry instruments specifically designed to search for these planetary resonances, adding yet another tool to the growing scientific toolkit for understanding worlds beyond our own. I hope you've enjoyed this journey through the physics behind the Schumann resonance, from the structure of our atmosphere and magnetosphere, through the mechanics of lightning and electromagnetic waveguides, all the way out to the tantalizing possibility of resonances on other planets entirely. It's a subject that beautifully ties together so many different branches of Earth science into one elegant, ever-present hum circling our planet. I'd be very pleased to hear your thoughts on this topic or your ideas for future geoscience videos down in the comments below. If you enjoyed this video, please consider clicking the like button and subscribing to the channel for more content like this. I've been your host, Stefan Burns. Thanks for watching.